Down south. That's not very often. Frazier Pruett. Yeah.
Josh said you were gonna check it as soon as I assumed he was gonna look. So.
Just give us the thumbs up. You need to put another cylinder. No,
I need 2 cents.
maybe.
You got a motorcycle. I do. That's all I got.
Oh, true.
I can. And I haven't missed the big thing.
Right. That's important.
Is this going out?
Yeah. It's live streaming and repeat this.
Do I need a mic?
It'll get picked up.
Welcome, everyone. Thanks for your patience. We had some tech stuff to get lined up. My name is Crystal Hopper-Meyer. Some of you may have already seen me before. I have actually moved into a different part of the college here, but I still oversee STEAM pathways. But I wanted to take a moment to first welcome you all here and say thank you for attending our first lecture for the fall. We're excited that you're here. We also have somebody that you're gonna get to know pretty good. Right here beside me is Cassie Coiner. Cassie is our new STEAM Pathways Coordinator. She'll be working with each of our professors on a variety of different activities, events like this one, and we do a lot of K-12 community outreach. Be looking for some, I think we have an upcoming, planetarium shows and things like that she's gonna share with you about. But I just want to take this time to welcome everyone and say, this is actually going to be the last time that I'll be doing this part too, because I'm kind of handing over to Cassie now. But I wanted to first say welcome Cassie to this part, and this is the fun one. So there you go. I'll see that.
Hello, welcome everybody. Like Crystal said, my name is Cassie Coiner. I'm also, you guys can tell, I am visually impaired. So this is a new experience for me. I have actually been in this position since July 15th. I made it through STEAM Academy and I am still here. So I call that a win. So nobody died. Yay. And I say that as a joke because we didn't come close to anybody dying. So anyways, all right. So I wanted to welcome you all here. This is my first lecture ever to introduce. A couple of things. This is our second week of term here at SWOCC. We are having our first SPEAR student research meeting tomorrow. So you guys will hear a little bit more coming out about that once we get that going. Those are going to be on Wednesdays at 3 p.m. So I do have some of my business cards up back at the table. If you guys are interested in any information about that, feel free to email or call my office. I'm happy to share some of that info. And then we have a planetarium show coming up on October 2nd. It's actually one of our students that are going to be putting that show on. She is a recipient of a Oregon Space Grant Consortium grant, and she has to do so many K-12 outreach events. So this is her program that she is putting on. So if you guys want to come out and support that, that's going to be at October 2nd at 6 p.m. And we're going to meet over in the PAC, which is the Performing Arts Center. So without further ado, since we are running a little bit behind, it is my pleasure to introduce Professor Frazier Pruett, who is going to be telling us a little more about part 2 of solar energy. And then at the end, we'll have some Q&A, and then we'll have some other stuff to follow up with.
All right, very good. Thank you, Kathy.
All right. All right, is this my clicker? Let's see. Guess not. I'll just do it the old fashioned way. Okay. This is the second and final installation of this series. We did part one, seems like a long time ago, it was January, as a matter of fact. And I appreciate those that came back and waited this long. I hope you remember what went on the first time. We can review that a little bit. We're not going to go over it in detail, but I may hit the highlights just to refresh your memory there. As you may have recalled, we are starting with the cell itself, and we learned a little bit about how they're made, how they work, a little bit about energy density that we are dealing with. Now, we're dealing with photovoltaic solar. Now, there are other forms of solar as well. There's thermal solar, and those, you can use that in a passive form to heat your building. You can use it in an active form to heat your water. That actually works. I haven't seen that recently, but that does exist and it does work. We know we get about 1 kilowatt per square meter every day of incident radiation from the sun. And without the energy from the sun, life would be pretty miserable here. In fact, it's kind of one of the key facilitators of that. So we can convert some of that energy directly into electricity. Now, we don't get 1 kilowatt per square meter. We don't recover that much. We get approximately 20% of that. In ideal conditions, and ideal meaning there's no cloud cover, there's no pollution, there's no obstructions on the panels. We're at the right time of year. So ordinarily we get less than the maximum that we could get. I'm going to just kind of skip through here and I'm going to stop here. Okay, you may have remembered this curve. So this is a curve of an array of cells. On the vertical axis is the voltage, and on the horizontal axis is current. And one thing this is actually looking at it for different incident radiation levels. So you can see that in the best case, we come all the way out here and we get, let's say, 8 amps. And this is just an example. But as there's less incident radiation, it kind of folds back. But one thing you'll notice is that the lines kind of go vertical as the voltage dips. And that kind of goes to the characteristic of these cells. They tend to look a lot like current sources. They're not pure current sources. They're actually voltage limited current sources. And we're going to use that fact when we put them into a panel. The other thing you're going to notice is they tend to hold steady for voltage until they drop. So there actually is a maximum power point on this curve. And this is now power on the vertical axis, looking at current on the horizontal axis. And you'll notice it looks like you kind of climb the mountain. And once you reach the peak, which is the maximum power point, it drops off rather quickly. So we want to stay at the peak all the time. And that's a little bit tricky in terms of the control algorithms. But there are a couple of ways that we do that. We won't necessarily get into all of the algorithms for that. Okay, so this is a model of a cell. You see it's modeled as a current source with a single PN junction diode in parallel with it. So the internal diode is actually in the silicon. That's what that cell is. It's actually a very large diode. And it's the simplest of all semiconductors. It's a PN junction. And that's what ultimately limits the voltage. Now the current source is directly dependent on the incident radiation on the cell. So the more light you shine on the cell, the more current you get out. And it'll either go out to the load or it'll be consumed in the internal diode. You follow the red arrow, that's with no loads consumed internally. Uh-oh. Okay, let's talk about panel characteristics a little bit. I know I went over that pretty fast, but we've got a lot to cover tonight, and I'd like to get to the end. One, so you don't have to wait 10 months to remember everything. So in order to construct a panel, if you looked at one, you might notice there are lots of cells in the panel. And those cells are connected in series. And one of the things I tell my circuits students, in fact, we talked about this week, is that in terms of combining sources, we don't series up current sources. That's generally a not a permissible type of connection. But in this case, the voltage is limited, unlike ideal current sources. So we have a way to get away with that. So we series these up because the cell voltage itself is something in the order of 0.7 volts. That's very low. So in order to get it up to a usable voltage, we need to add these in series. But they still carry the characteristic of a current source. So if you short them out, which is actually a fairly benign condition for those, normally you don't short out a power source. But for current sources, that's actually very benign. It isn't for voltage sources because generally voltage sources have a lot of current potential. So we connect them in series, and it's not the best way to use them. Because if we could use each cell, if we could convert the power of each cell and then combine it, that would be a more ideal way to do it. Unfortunately, the efficiency of the conversion would be prohibitive. So we're going to talk about inverters, how we get from panel voltage. By the way, panels put out DC. They do not put out AC. We have to use a device to go from DC to AC. We'll talk about that as well. But to get a high enough voltage, we have to put these in series. So that's what the panel does. These are a couple of different kinds of panels, monocrystalline, polycrystalline, and thin film. They each have their advantages and disadvantages. Thin film is the most different of the three. It has a much higher voltage, but it has some other bad characteristics that make it maybe not the best choice. The others are made up of silicon. I don't know if you know how silicon is made, but it's grown as an ingot in a foundry. Starts out with a crystal, and they draw the crystal out of molten silicon, and it grows an ingot. Then the ingot comes out, and then it's sliced into very thin wafers. And then those are polished, and they turn those into cells. Now, the good news is the cells don't have to be particularly high quality to be useful as solar cells. For other types of electronic semiconductors, they need a very, very clean process. In fact, they make these in clean rooms, and they'll call them say a class 1000 or a class 100 or a class 10. And that means that has to do with how many parts per million particles are in the room. And those particles become contaminants when they make a semiconductor. But the good news is solar cells can be made in a fairly dirty environment, not really dirty, but much dirtier than others. So that affects the cost, keeps the cost down. Here's a little bit of a comparison about the three. The monocrystalline have the highest efficiency. Cost is kind of in the middle, and they have the longest life. polycrystalline, medium efficiency. And what I mean by efficiency is how much power you can get out of the cell versus how much incident radiation you have. Because when it comes to solar power, it is all about surface area. So the more surface area you have, the more energy you can harvest. Perhaps you've seen some large installations that have been installed where there's rows and rows of solar cells. If you go up to Portland, where 205 and 5 split, there's a large array there. In fact, if you're so interested enough, you can actually dial in to their data aggregator, and you can see in real time what that array is putting out. So it's been there for more than 10 years now. It was new in around 2009, or maybe 15 years or so. So that array has been there as a test. And it's kind of in space that's not used for anything else anyway. So that's one of the good things about it. Thin film has the lowest efficiency. It has the highest cost and the shortest life, which is why it doesn't get used that much. Yes, any questions? I feel like I'm going fast. If I'm going too fast, stop, raise your hand, and we'll talk about it. Okay. So cell, plus, somebody? No? Okay. So cell count in the panel is always divisible by 3. Why is it divisible by 3? Typical cell count numbers would be 54 or 60 or 72, and that's how many cells are connected up in the panel. So, and these are called substrings. They have 3 substrings. And the reason we have 3 substrings, we're going to find out that these current sources, all connected in series, are always limited by the cell that's putting out the lowest current. So whatever the lowest current output is from any cell limits the output from the entire panel. So if you were to lose 1 cell out of 72, that's something in the order of what? 1.5%. You don't lose 1.5% output, you lose everything. So this is what makes it kind of ugly. So in order to deal with this problem, we put in what are called bypass diodes. So when a particular cell is underperforming compared to the others, its voltage will tend to collapse, but there's a diode that steers current around it. So it allows you to get power from the other cells. Now, because it's not on a single cell, it's on a substring, you'll lose 1 substring. And you'll still have 2 out of 3. And if you lose the other 1, then you'll have 1. And ultimately, if the panel gets shaded too much, you'll lose the entire panel. So it's just kind of a compromise we've had to make in order to make this work. Connecting these up, I kind of threw this in here, an MC4 connector. Probably nothing that means a lot to you, but it is an industry standard. And that's a picture of it. You'll notice that it has a latching mechanism, so they don't come apart. It has a little Viton seal on it to keep water out of it. Now, keep in mind, these installations are intended to last 20+ years. So generally, they're low maintenance. Now, you may have to go out there and clean your panels off. If there's any dirt, leaves, anything that blocks the panels, you're going to want to get that off of there. Now, even if you were to go into the desert, you have problems with sand. Blowing sand will tend to frost the glass, will also accumulate on the panels. So even the desert is not necessarily the ideal environment. So debris on the panels is a big deal. Yes, sir.
Two questions. You mentioned cleaning the panels.
Right.
So what is the kind of the best mechanism for cleaning the panels, and then just kind of an aside and an example that comes up when you're talking about sand covering things in the
Yeah.
desert. That's actually a couple of the ways that two of our Mars rovers died, is eventually it was sandstorms on Mars that basically
killed them.
shielded out their solar panels and they couldn't get power anymore.
That's right. I get that. So around here, a typical cleaning might be just hosing them off. Now, these are glass. So you could use anything that you would normally use to clean glass. Now, I know in places where these are in the desert, they actually have robots and their job is to clean the panels. So now, once they're frosted, unfortunately, that's a permanent thing on the panels. Once the surface gets pitted because of blowing sand, that's a problem. There is no, I don't know of anybody that goes out there and tries to repolish the panels up. But if it's just debris that's landing on the panels, they are waterproof. You can clean them with ordinary soap and water. Now, if they're on your roof and you don't want to climb up there, you might have to, pay a service to come out and clean those off. But the surface is glass. Plastic will just not hold up over time. That's a problem with plastic. So they are glass. They are sealed against weather. Unfortunately, they're also in a very harsh environment. They're going to get the heat of the day. They're going to get wind. And one of the big killers of anything electronic is thermal cycling. So they're going to go through the heat of the day and they're going to go through the cold of the night. The thermal cycling, yes, sir.
Could you run a small lighthouse with the solar panel?
Help me understand the
There's a
small.
replica of a lighthouse in Mingus Park in the pond,
Yes,
and we were saying that if you put a little solar panel on it, you could run the lighthouse.
the answer is in principle, yes. You might not like the size of the solar panel you have yourself. So just to give you an example, an ordinary panel that you might go and buy is going to put out, the largest ones will put out in the neighborhood of 400 watts. And of course, at night, well, you don't have any light. So you're going to need some kind of an energy storage mechanism for that. So you might find out that the solar array that you have to put out there to run the lighthouse is bigger than the lighthouse. So,
And they don't have any smaller.
oh, they do, but with smaller panels comes less power. So, I mean, that's kind of the trade-off there. So,
That's something we were thinking about. What they should do is put something for that lighthouse.
yeah, I've had people go, well, why don't we just light up something and shine it on the panel? And, well, yeah, there's no violating the law of conservation of energy, I'm afraid there. So, and given that the conversion is about 20%, it wouldn't go very far. So, you could put solar panels out there to do specific jobs, and they are in remote locations. So if you were going to build a house that is off grid, you might want a solar array out there to give yourself some power. So that's actually a really good use of solar panels, but you don't have a grid as backup power, so you might need some other backup power like a generator or something like that. So these connectors, there are lots of manufacturers for them. They've been around for about 15 years now. Typical wiring for this is 10 to 12 gauge wire. And these connectors only have a mating life cycle of about 10 mates and unmates, which is kind of small. But if you consider once they're assembled, they're not intended to come apart. You're not going to move your solar array typically. So just to give you another example, your standard USB-A connector, those are also rated for a number of insertion cycles. And it's an appallingly low number. It can be as low as a few thousand. They can have some higher life ones. So what that means is when you go to the airport, you plug in your phone in one of those kiosks, well, you can bet that most of those connectors are worn out because they probably exceeded their life cycles in a week or two. So anyway, did I answer your question, Dr. Plum?
Yeah.
Okay. Don't want to move on till I covered all the bases there. Okay. Now it's backed up. Okay. Solar panels do decrease their output over time. It's not horrible. It's something in the order of about 0.5% per year. So in 20 years, you're going to be down about 10% from the installation. Now, the one good thing about solar panels is manufacturers guarantee output of the panel. And it's usually plus something minus nothing. So if they say it's a 400-watt panel, they guarantee you can get 400 watts out, maybe a little bit more. But it is kind of a numbers game. They may match cells to make the panel particularly efficient. And the rate of decline, unfortunately, is temperature dependent. Heat is one of the big killers of electronics. So anything that gets really hot and it's electronic is going to have a shorter life. So, and solar panels are out in a harsh environment. So it may interest you to know, you might think, well, Arizona, that's a great place to put solar panels. There's a lot of sun in Arizona, right? That's true. Well, there's also a lot of dirt in Arizona, and it gets really hot. So solar panels are rated to withstand for 90 degrees C on the backside of the panel. And I know that because I work for a company where we had to design a junction box with electronics in it to go in the back of the panel. And it had to live in a 90 C environment, which is really hot. So, yeah, a lot of heat building up, particularly in Arizona. It may interest you to know that we can get nearly the same yield on our solar panels here because we're so much cooler here than Arizona. Yes, Arizona is further south; they get more, more sun, but we have cooler temperatures here, which tend to offset that to a large extent. Okay, let's talk about the junction box. I mentioned those, and you'll see here, this is a picture of a 3-string junction box. And down here, you see, you may notice the little triangles with the lines, okay? Those are diodes. Now, a diode, if you're not familiar with them, are kind of like a check valve in a water line. So they prevent current from going in one direction and they pass current in the other direction. So that's what diodes do. So when a cell collapses, when a substring collapses, the diode gives a path for the current from the other cells to go around it. So you don't lose the entire panel. You'll lose a substring, but you won't lose an entire panel. So that helps to improve your energy harvest. Now, the diodes have to be rated to take the full current, and they don't have to be particularly high voltage because a substring might be 25 or 30 volts. So your average panel, let's say of 72 cells, if you consider they're 0.7 each, you're somewhere in the neighborhood of 50 volts, the open circuit voltage. Maximum power point on those cells is about 80% of the open circuit voltage. So, and there are actually some algorithm to base their maximum power point tracking on that 80% number. Turns out it holds pretty well. So the junction box is mounted on the back side of the panel, and you can see that it's plastic. And it's literally glued to the back side of the panel. So all of the substrings are routed to the junction box. And you see where the connections are at the bottom. Those are called glands. And the cables, the red cable's the positive one, the black cable's the negative one. And with the MC4 connectors, they are, in principle, they need to be put on correctly so they're in the right orientation. So in principle, they're not necessarily keyed to the wire, but as a matter of practice, you have to put the right end on the right polarity so that you can just plug them together. If you get them wrong, you may end up plugging in something backwards. So as the installer, they're supposed to know which way to put the connectors on. So, and if you are interested in doing something on your own, you can buy these on Amazon. In fact, I've done that. So, and you can get a crimping tool. These things aren't horribly expensive. And they are pretty good connectors. You might even find some other applications for those. Talked about the shading problem. So here's an example. This is kind of a simplified model here. We only have 4 cells in it. And they each put out current. They each have an internal diode. And when we put them in series, we multiply the voltage. And the current's going to be limited by the lowest current output of any cell. So the current goes out, goes to the resistor load R1, and it doesn't have to be a resistor. It could be a, I'm just using that as an example. Okay, in principle, you would have some kind of a way to convert that to AC. So if one of these gets shaded, as I mentioned, you don't lose 25% of the light. You lose, or the power, you lose it all. And that's one of the nasty things about series connection for the cells. If we could connect them in parallel, it'd be much better, but fortunately the voltage is much too low to be useful. So this is where our diode helps us out here. The diode, you follow the red line, and it's connected in parallel with the cells. Now I've shown it connected in parallel with each cell. In principle, it's only in actual panels, it actually bypasses a substring. And a substring would be, well, let's say if it was 60 cells, one substring would be 20 cells. So it would bypass 20 cells. And if our bottom solar cell was not putting out any power, we can bypass it and get power out of the other 3. That's how the diode helps us harvest more energy. Otherwise, solar panels would be highly impractical if we couldn't do that. Now, what if we have multiple strings? So in each cell, now imagine that these are solar panels rather than individual cells, because that's what happens in a large array. You have your one solar panel is going to be connected to another solar panel. And by the way, mixing and matching solar panels is not a good idea because you're going to be limited by the smallest panel. So you're going to want your panels to be matched, at least the same manufacturer, the same model. If you put one in there that's a different size, it's going to limit the output of your entire array. That's not a good idea. So if you're going to buy panels, you want to purchase them at one time. You don't want to kind of do it over a period of time, because also you're going to run into degradation. So the output of the older panels is going to be less than the new panels. So if we have multiple strings, and this is entirely possible, for utility scale arrays, we have in the US, the maximum open circuit voltage that's allowed is 1,000 volts. So if you have a panel that say can put out 50 volts open circuit, it means you can put at most about 20 of them in series. Europe's a little bit higher, they're 1,500 volts. So the way you keep adding panels to your array is you have more strings and you put the strings in parallel. So you can't keep going up with the voltage, but you can add another string of panels. Now, it's also a good idea when you're putting panels, strings of panels in parallel, you want to match the number of panels in each string. You don't want one with 10 and one with 12. Okay, because what's going to happen is the 12 is going to kind of cut off the 10. So you don't get the advantage that you would. So you do have to kind of balance things a little bit. But you can see what can happen in a case like this. Now, the internal diodes are actually real. They are real diodes. You can back drive current into a solar panel. So if I had a solar panel here, I could hook up a power supply and I could put current into that panel. Now it doesn't produce light, okay? In fact, it'll produce heat, but it will conduct in the reverse direction. In fact, that was one of the ways we simulated sunlight. If you're developing a product for the solar industry, you're going to want to be able to test it. You may not be able to depend on the sun every day, particularly in Oregon, right? Rains a lot here. So if you want to test it under different conditions, you need to be able to simulate that somehow. So the best simulator for a solar panel is a solar panel. So we take panels and we drive them with current, and we can simulate the effect of some that are getting more sun than the other, or how much current we put in them. So that's a way to simulate our solar array without having to depend on the sun for that. Anyway, so you can literally, one string can back drive another string. So instead of putting power into the load, it puts power into the other string. So what do we do about that problem? Well, more diodes to the rescue. Okay, we put in more diodes to prevent backfeeding a panel. So you notice we added 2 diodes at the top. So current can come out of a string, but it can't go back in. So it has to go into the load. So now we have a case where we're capturing as much power as we can. So you can see that the whole shading thing is really rather complicated problem. So when you select a site, or somebody helps you select a site for a solar array, you have to consider things like trees, time of year. We're going to talk about where you might want to put a solar array. The other thing you have to consider is your latitude. So if you're in Arizona, you're at lower latitude than we are here. We're something below 45 degrees. Maybe Dr. Pointer knows exactly what our latitude is.
It's about 43.4.
That's pretty accurate. Okay. So we're about 43 degrees. So the further south you go toward the equator, the less you see in terms of seasonal changes. But we live where we live. So, okay, so shading is a complicated problem. And keeping your panel clean. Now, they don't have a lot of maintenance on the panels. Generally, now, do they fail? Sure, sometimes they fail. And that usually means the seals get broken on the panels. And you start to get moisture in there, and the moisture starts to corrode the connections. And the panel is no good anymore. Now, the good news is panel manufacturers warrant them for 20 to 25 years. So that's pretty good. So if one goes bad, now, having said that, that may not cover labor to come out and replace the panel. They'll give you a new panel, but it may be up to you to pay for the labor to get that done. So that's something to watch out for when you look at the warranty on this. Okay, maximum power point tracking. Touched on this earlier. So you always want to operate your array at the maximum output, and there is a maximum. In fact, we're going to see you could have two relative maximums in the curve. And that can get complicated for inverters to track those maximum power points. Because depending on the algorithm they're using, they may get stuck at the wrong one. And they don't know that there's actually a higher output. So this gets to be a rather complicated problem. How do you break out of that? So one of the things that we thought about doing when I was at a company developing a microinverter was to periodically sweep the entire panel to find out if the maximum power point has moved. Now, while you're doing the sweep, you're not harvesting a lot of power, but you are looking for the most optimum place to operate. And that could change depending on what the conditions are. And this is particularly true when there are shading things happening. So as output goes up, you see it goes up rather gently. And once it reaches the maximum, it kind of drops off rather abruptly. Okay. From a control point of view, that's really hard to deal with, because what's happening is the slope of the curve is changing rapidly, and that gets very hard to track. We're trying to balance right on the top of the curve, and if you go a little bit too far in one direction, it'll just collapse on you. So, and when that happens, your inverter might go off, and then it has to go find the maximum power point again. So tracking that is tricky business. Now here's an example that shows multiple maximum power points. And this is based on mismatching of the strings. Now these are based on some simulations I put together just to kind of demonstrate the point that if you have multiple strings of panels, if they're mismatched by 25%, you see that you have two maximum power points at the top. And in fact, they're not all that different. So it might pick one or the other depending on where it wants to operate. Now, if the mismatch gets to be much bigger, you can see in the bottom one with a 75% string mismatch, you have another relative maximum power point, but it's much lower than the big one. Now the inverter could get stuck at the wrong one. So this is a problem that the inverter manufacturers have to deal with. So you always want to be operating at your maximum harvest. Now, for many years, we didn't have any on-site energy storage for output of the solar panel. So the way the architecture was, the solar panels were connected directly to the inverter. So they would convert panel energy directly to utility power in real time, which means that as the panel output changes because of clouds or birds flying over, the inverter has to try to track those changes. And what that means is that you're putting out different power over a short span of time to the utility. And that's not what the utilities really want to deal with, okay? One of the things that's difficult for them to manage is distributed power because they don't own it and they don't control it. So this makes them guaranteeing power quality to all of its customers, a very difficult thing for them to deal with. So as long as distributed energy is a fairly small percentage, it's a manageable problem for them. But if it were, say, 50% of grid power being used, it's a big problem for them. Because again, they don't have any way to control the output from your array. Okay, and they are obligated by law to buy your power. And we'll talk about that a little bit too. That's wrong. So, talked about techniques, our algorithms. These are a couple that are commonly used. The one that's most commonly used is what we call perturb and observe. So in a case like that, the inverter will move in one direction or the other to see if the power is increasing or decreasing. So, you know, it's trying to stay on top of the hill. So it's going to look in one direction and see if the power is better, it keeps going. If the power is worse, it goes back. So it's always hunting for the optimum place to operate. The 80% rule, 80% of open circuit voltage. So when the panel is not loaded, that's the open circuit voltage. It'll measure what that voltage is and say, we're going to load the panels down to 80% of that output. And that's where our maximum power point is going to be. Now, you might think, well, that's kind of short-sighted, right? Things can change. Well, it turns out that 80% number holds pretty well. So, and I know companies that do that. Incremental impedance. So what that means is that the impedance of the panel depends upon the incremental change of voltage with respect to current. So what they're looking for is basically a zero change. They're looking for a zero change in voltage. So for a given current, they're looking for a zero change in voltage. That one isn't used as much as it used to be. And these are all different techniques for finding the maximum power point. Now, having said that, these are almost always done using some kind of computer algorithm. It's really difficult to try to implement this in hardware. There are some hardware solutions for that. But computer programs for control have the ability to do things that are non-linear, which is very hard to do with hardware. So computer algorithms can look at where you're operating. They can look at how things are changing, what trends are. So that's pretty much how they're all done now. Okay. Before we go on to PV installations, any questions about panels or shading, maintenance, installation, anything? Yes, sir.
So I live in Vegas, and I'm now understanding. So if you mentioned how very high temperatures affect the panels in the negative manner, why would it be beneficial for someone in Vegas to get solar panels? Because there's a lot of people operating them.
That's true. Now, having said that, that doesn't mean that they're not useful, but it does mean you might be losing 15 to 20% of the available, let's say, under ideal conditions, 15 to 20% of the output. So, is that still worth it? Probably. I mean, if you lost 90% of the output, yeah, that's a problem. Okay. Now, there have been, having said that, and we kind of brainstormed, you know, what can we do about the heat of the panels? And we actually thought about using solar panels for thermal solar as well, because they get hot. What if we coupled them up to some heat exchanger where we could use the heat of the panels to heat water? Sounded like a good idea, except that you're mixing water and high voltage. Right, so maybe that's not such a good idea, but in terms of recovering energy, that could really work. You're able to get heat out of the panel, you cool those down, heat your water up. So far, I haven't seen anybody actually try to implement that, but that's one of those ideas we kicked around about how to make the panels more efficient. Because not only are you going to get electrical power, you're going to get thermal power. So it's kind of a win-win. So, yes, sir.
Are most panels made in China or they made in a bunch of different places? And are there certain ones you can steer clear of?
The answer is, yeah, there's a large number of them made in China. In fact, there was a big problem with, I think the Federal Trade Commission went after China for dumping panels on the market. Gosh, that's got to be over 10 years ago. And a lot of those companies have gone away. I don't have any names of ones I'd say, hey, don't buy those panels. Again, if you buy from an installer, the installer should stand behind should be able to honor the warranty claims on them. So, but you have a lot of leverage in getting a manufacturer in China to make good on their warranty. There are some that are credible, and will do that. But then there are some that, they come and go, right? They make up some product, they sell it, and they're gone. So, and as far as making them in China, the unfortunate thing is it all comes down to cost of materials and cost of labor. So making those, in places like America or making them in Europe is really cost prohibitive. So it's kind of where we're at there. So. Any other questions? Yes, sir.
The seals, you mentioned that these are sealed panels,
They are.
and sealing in a lot of instances, especially with a lot of heat and cold cycles,
Yes.
fails.
Yep.
What happens when the seal fails?
You get moisture inside, and that will degrade connections that will attack the solar panels, and eventually you'll end up with failed panel. I have actually seen how they make these. They are kind of laminated. So they take the glass and the backer and the solar cells and they kind of laminate them together. But you're dealing with materials that have different coefficients of thermal expansion. Usually have an aluminum frame that they sit in. So yes, with enough thermal cycles, it's going to damage the panel, and they do fail. In fact, there have been instances where they fail and they will begin to arc. You may recall I said panels tend to act like current sources. Well, guess what? What else acts like a current source? A welder acts like a current source. So you can actually have fires start because of that, and that's actually happened. So another thing we were kind of looking into was arc detection. What if you start get arcing on the panel? Can you detect that? Well, it's a stickier problem than you might imagine. So, but the answer is panels fail, and when they fail, hopefully they don't catch anything on fire, but they'll just have to be replaced. Now, if you're hiring an installer, you may have to hire an installer to change out the panel. So,
So to avoid mismatch, should you have spare the same batch?
Depending on the age, if this happens 15 years after the installation, the chances of getting a matched cell is pretty small. The manufacturer will provide whatever it is they're making at the time. And in principle, it would be similar. So in terms of buying panels and saving them in case you needed them. I mean, you can do that. But truth is, if you had extra panels, wouldn't you use them to make power as opposed to just storing them away? So. Yeah, yes, you can do that. Nothing wrong with that. But whatever panels get replaced, they're gonna be replaced with whatever's available at the time. Other question? Good question, good question. Okay, let's talk about installations. All right, so I've already used some of these terms. Inverter, what's an inverter? So an inverter is an electronic power conversion device that converts DC into AC that would be compatible with the grid. So the panels put out DC and it gets converted to AC. And there are quite a bit of requirements around that. One of them is, let's see, grid tie. So in order to connect to the grid, one, it has to be an installation that is been put in by an approved installer. So by the way, not every electrician is approved for solar installation. It's a special certification they get to do that. It's a special part of the National Electric Code. And the inverter is going to connect to the grid. Now, one of the things about that is we're going to talk about standards here, but the standard in North America is the inverter has to wait 5 minutes to make sure that there's a valid grid there before it connects. So what that means is every time your inverter goes offline, it's going to wait 5 minutes to make sure there's a good grid there. Now that can be tricky business too. And we had some algorithms for determining if the grid was real or not. So because you have to put power back in the grid that's compatible with the grid. One of the compatible things is distortion. You're allowed 4% total harmonic distortion in your inverter, which is usually not too difficult to do, but you can't distort the power lines. Also, inverters are not allowed to drive reactive loads. So they're always looking for, the inverter has to operate with a power factor of 1. And the reason for that is if it's going to drive reactive load, it has to have more energy storage in it than it would have to have otherwise. So that's what we call grid tie. So if you're going to tie into the grid, regardless of your how you're monetizing your solar power, it's going to have to meet the grid tie standard for North America. Okay, anti-islanding. Okay, that has nothing to do with being against islands, but what it means is when the grid goes down, so does your inverter. That's a very important reason for that. When the power company sends out line crews to work on the power lines, they always work under the assumption that everything downstream from the source is dead. You don't want sources downstream that are back feeding, because that creates a hazardous condition for the people working on the power line. So they call that anti-islanding. So if the grid goes down, your solar array has to kick offline. Now, how does that work if you're doing a, let's say, off-grid situation? In a case like that, there's no grid to connect to, so you don't worry about that. You can have a standalone system that is yours, and most inverters that we looked at have a way to configure them to work without the presence of a grid. So the inverter becomes your source of power. And that's a case when you're not connected to the power grid at all. So that is a way you can use your solar power. What else? Solar harmonic distortion, power factor, talked about those. Okay. Now, types of inverters. The isolated string inverter. So when I say string inverter, it means it's operating from a string of solar panels. Maybe 10 to 12 is a pretty common number here in the US. So the input to that inverter is going to be, could be as high as 1,000 volts. And it's going to convert that to AC power that's compatible with the grid. And it's going to deliver it in real time. Now, what makes it isolated is that the converter inside is through a transformer, which means that the solar panel is not directly connected to the power. Call this an isolated string inverter. The advantage to that is less of a shock hazard. Now, it is permissible to have a non-isolated string inverter where the solar panels feed the inverter. There's no isolation mechanism, and it directly sends power out to the power line. This is a completely permissible configuration. Now, why would you pick a non-isolated one if you could have an isolated? The big reason is it's more efficient. Having that transformer in there costs you a little bit. It might be 1 or 2%. Now, how efficient are inverters? The best ones are in the 98% range. It's pretty good. Converts 98% of solar energy into usable electricity. While let's say an isolated one might be 96%. Now, do you care about that? Well, you're going to have to do the math on that and say, is 2% worth it? You're also going to end up, because there's a big transformer in there, it's going to cost more and it's going to be heavier. So are those things you care about? Maybe, maybe not. Okay. But that's a choice you have to make. And the installers will typically talk to you about the pros and cons about these things as well. Now, another thing you're probably going to want to do is you spend all this money for a photovoltaic system. You're going to want to see what it's putting out in real time, because that's why you're doing that. So we call that data aggregation. So it's not uncommon to have some way to find out what your inverter is producing at any given time. That can be done wirelessly, Bluetooth, Wi-Fi connection. All of these things exist out there, but you can do that with. So you want to monitor. Now, I heard stories in Germany where they were selling these systems to farmers. They were converting their land from agriculture to basically turn them into solar farms. And their production was electricity. And they would be watching what's going on with the outgoing electricity, because that's what they're selling. So if that's, the installer will usually give you an expectation. This is about what you should be able to produce. Now, for the average house, you probably end up with a system that's in the 3 to 5 kilowatt. That's pretty typical for a house here in the US. If you have a bigger house, it might be bigger. If you had a commercial building, it might be bigger yet. So that's about what you need to operate your house for electricity. Now, if you're tied to the grid, well, if it's more than your solar array is putting out at that time, you'll just draw power off the grid kind of seamlessly. Okay. Another possibility, and this one was one that I actually had some experience working on the development of, something called a micro inverter. Now, it's not as micro as it sounds. So, and the idea is that you would have an inverter that connects to a single panel. So The inverter would mount on the back of the panel or somewhere in the array. It's also outside. And it would not take input from a single panel. Now, the advantage to that is you don't have to worry about what's going on with the other panels. That one panel will produce output. And if the other panels go down, they don't all go down. Now, the upside, you do have redundancy, but what you lack is now you have a lot more electronics in your array. And those microinverters are outside, they're mounted behind the panels. Means they have to live in a very hot environment. And the chances of having one fail is much higher. Because it's in the rain, it's in the heat, it's in the cold. But it also means you can build your system incrementally. As in principle, you could make as little as one panel. Now you still have to have it connected to the grid, and you can add another panel. It's also a way to mix and match panels. Because you're only connected to one panel, it's not dependent on what's going on with another panel. So if you were building a system that you're going to build over a period of time, and you might have different panels, it's a way to deal with panel mismatch. So that could be an advantage. Now, again, more electronics, more likely to fail. Now, string inverters don't exist outside. They typically exist, let's say, in an environment that is out of the weather, but maybe not controlled. That'd be like a garage or an outbuilding. So they're not in a hot environment. They're going to be sheltered from the rain, but you may get the extremes of temperature because they're not in an environmentally controlled facility. So that's actually good for the life of the product. So those are the kinds of inverters you can get. Okay, these are some of the standards that you're going to run into. IEEE 1548 is the grid tie standard in America. It's actually called out in UL 1741, which is the general standard for solar type products. UL doesn't actually call out, it actually refers back to IEEE 1548. In Europe, you're going to run into these IEC standards for 62109 and 62103 would be standards for electronics on the panels. That would be including microinverters or big power inverters. It might be just a device that is measuring voltage and current of any given panel. Let's say you have an array out there, you're going to kind of want to know what each panel is putting out. Now, kind of getting back to the microinverters, you kind of get that for free because each microinverter is going to monitor what's going on with its panel. In a string, the string inverter doesn't necessarily have visibility to any given panel. So you may have to put on a communications device that's monitoring every panel's output. Typical kinds of communication would be either wireless radio that has its problems. The other one is power line communication, where the signal goes out over the power line, which is kind of what the power company does with your electronic meter. They talk to it. And these are not very fast communication paths. The data rates are pretty slow, but these are slow moving events typically, so that's not generally a problem. IEC 61730 is the European standard for panels themselves. IEC 61216 is the installation standard in Europe. Now, we don't care too much about what goes on in Europe, but if you're a manufacturer, ideally you don't want to make product that is location specific. You'd like a product that can be, that appeals to a worldwide market. So that's why as a manufacturer of panels or a manufacturer of inverters, you would want to meet all of these standards. So you don't have to have a North American model, European model. So. And you can look these up. The other one I didn't touch on was the National Electric Code Section 690. You can actually go out online and find a copy, maybe not the most current copy, but you can get a copy of the National Electric Code if you want to know what the requirements are for installation. There are mechanical requirements as well as grounding requirements. Generally, they require you to ground your solar array somewhere. They generally don't want to be floating with respect to the earth. Okay. Efficiency. And we talked about efficiency of the inverters being in that 96, 98. Now that would be like at max output. So there are two weighted standards for efficiency. One is from the California Energy Commission and one is from the European Union. So they recognized early on that the chances of your solar array operating at max power is almost zero. In fact, you're going to operate at some reduced output. So in order to kind of tell the consumer, you know, it's like the horsepower rating of the engine in your car, 400 horsepower. Well, yeah, when you put your foot in it, it's 400 horsepower, but you don't live there. You're living at a much lower output. Well, that's true with solar panels too. They live typically a lot lower than that. Now, the California Energy Commission has their weighted standard, the EU has their weighted standard. So when they tell you what the efficiency is, you want to know, you know, in America, we're going to look at the California Energy Commission in the EU. Now, there are no requirements, but there is a method for making these. Now, here's the weighting. So you can see that the inverter output as a percentage goes from 5 to 100. Now, for the CEC, you can see what percentage of the weighting. You can see it's maximally weighted at 75% output. Now, for the EU, it's maximally weighted at 50% output. It's a bit more conservative. And you can see at 100% for the California Energy Commission, it's only weighted at 5%, which means they really don't expect that to be operating at 100% output. Europe, they're a little more optimistic about their 100% output. So, and you can see that there's some weightings they don't kick in at all. So 5% is pretty low. 5% would be, you know, at the extremes of the day, morning or evening. Okay, questions about inverters or inverter weighting or anything like that? Now, when you buy microinverters, there are a few big companies. And when we were developing a microinverter, we recognized that at least one of those companies was using parts that had a known wear out mechanism for 10 years. They were using electrolytic capacitors for energy storage. And electrolytic capacitors are one of the few electronic components that actually has a known wear out mechanism. And the hotter it gets, the faster it wears out. And our reliability engineer predicted that they would have to start replacing these units after 10 years of life. And that's exactly what happened. So the microinverter manufacturer is going to want to warrant these things for as long as the panels are. You don't want to have to go up there and start replacing components, right? You want the system to have a life that's for everything in the system, not one that lasts a year and another that lasts 20 years. You don't want to have to go buy new inverters. So they warranted theirs for 20 years. Honestly, kind of banking on the fact that they would have a better solution and might not have to replace so many microinverters. Unfortunately, the name of that company is Enphase. They're one of the biggest in the industry. They're based out of Bay Area. So now they're still producing product, and as far as I know, they're honoring their warranty. So, but again, just because they'll replace your inverter doesn't mean they're gonna pay for somebody to climb up on your roof and do the work there. That may be on you. So compared to the cost of the inverter, that actually might be more. So gotta pay an electrician to go do that. Okay,
Great.
yes, sir.
When you go into, when you talk about the max power output, you're dealing with kind of the overall max electrical power after we take into account the efficiency of the conversion from solar energy to electric power, because I know a lot of like the solar kind of stuff has really low efficiency in that regard anyway.
Yeah,
So I assume we're already dealing with like 95-98%, it's basically 90 to 99% of what we would expect the max electrical power requirement, not necessarily how much of the sun's energy we're converting it.
well, the efficiency of inverters is pretty good. So even at low outputs, it's pretty good. So one of the ways we deal with low power output. Now, as we reduce the power output of any conversion device, the efficiency starts to drop off. Now, I like what we've done with battery. We play games with the operating point. In other words, so if I know that at 10% output, I'm no longer at 95% efficiency, I'm at 75% efficiency at 10% output. The game that we play is the same that's played with the batteries, is we operate at 100% for 10% of the time. So that's how we get to 10% output, and that's how we keep the efficiency up. So with batteries, the way the game is played with batteries, if you remember way back when phones came out, you know, they'd last for 2 hours or so. Well, right now what happens is your phone will go out there and ping to see what's going on and then shut down. So it operates for a very short period of time and then goes back into sleep mode. That's how we extend the life of the batteries. So it's kind of a game we play with that, so.
And that makes sense from that perspective. I was just drawing the distinction between the efficiency of converting the electrical power once you get to that versus the efficiency of pulling in energy essentially from the sunlight, from the initial source.
Right. So that kind of gets into why the standard was created in the first place. So if we didn't have a weighting for lower percentage of converter output, and we said, okay, we're only going to rate the 100% number, and you know, you're going to get what you get at lower percentages. It kind of is misleading to the consumer about what the real performance is going to look like. So if now the number weighting, so whatever the efficiency is at 10%, you multiply that by 4%, and you do that for every operating point, and then you sum it up. That makes sense. Okay. So that's how they get to, when they say the CEC efficiency, it means they've operated at all those operating points, and then they've summed it up and they go, okay, the CEC efficiency is, you know, 93%. And so you know that based on the operating points, they have considered that. Now the EU efficiency is going to give you a slight. So it's a way to kind of be more transparent about what you're really going to get, because these systems aren't cheap. So, and when you pay all the money, all that power matters to you, because that's money you're not recouping. Okay. Okay, energy storage. Now, you may recognize this as a sine wave, and in fact it is. And it's actually a power sine wave as opposed to a voltage or current sine wave. Now, the reason it's a power sine wave is because I want to talk about energy. So one of the things we have to do, now the red line in the middle represents average power. In this case, I've set that equal to 1 kilowatt. It was just arbitrary for this example. Now you'll notice that there are 2 peaks here. And if we go out here to about a little over 16 milliseconds, okay, that's 60 hertz. So that's the power, the frequency of our power grid, 60 hertz. So there are 2 power peaks in a line cycle. You have one on the positive half of the sine wave and one on the negative half of the sine wave. Now, the reason it's always positive is because when it's on the positive half, you have positive voltage and positive current. And when it's on the negative half, you have negative voltage and negative current, which is also positive. Okay. So we're talking about instantaneous power in the blue curve there. So when as it turns out, the peak to average power of the sine wave is 2 to 1. So at the peak, it's putting out, or you're generating 2 kilowatts. And then it drops down to 0, and then it goes back up 2 kilowatts. So when you have excessive output power, that energy needs to be stored so that you can use it when you drop below the average line, because the area under the using energy stored curve and stored energy curve are equal. Correct? So you have to store energy and then you have to deliver energy. And this happens at the line frequency rate. So in order to do that, we need to have something that stores energy. So in electrical engineering, we have a couple of devices that fill that need, or ones that we can talk about. So our energy storage, whatever it is, needs to have a long service life. Okay. It has to meet the environmental requirements, which means if it's on the back of the panel, it's got to operate in a 90°C environment. That's difficult. And the energy storage needs to be efficient. You want to, otherwise, you're going to be losing energy. And you do have some size constraints, right? So we have about 3 devices that will meet that, or have the chance of meeting that. The first is capacitors. Capacitors store energy in the E field of the capacitor. Inductors store it in the magnetic field or the H field, and batteries store it as chemical energy. And then you recover that. Now, the good thing about battery technology has gotten a lot better. We now talk about lithium batteries for just about everything now. The thing we have to be careful about when we talk about lithium batteries, there's at least 6 different chemistries of lithium batteries. And they range from very safe to very volatile. Okay. Now, going along with that is the very safe ones have the lowest energy density. And the very volatile ones have the highest energy density. So the lowest energy density would be lithium iron phosphates. Those are very hard to catch fire. Some of the other, the NMCs, nickel, manganese, cobalt. And those are the ones that are starting to get traction now. They're better than the lithium iron phosphate. And they're also relatively safe. So if you got a hand tool with a battery, it's probably got that technology in it. I know the car manufacturers are starting to put that in the electric vehicle. Anyway, so storing energy in batteries. Now, lithium batteries, as it turns out, are very good at storing energy. You get back about 99% of what you put in. That's really pretty good for a battery compared to lead acids or NiCad, some of the technologies of old. They're quite good. Inductors, they don't store a lot of energy. And they don't necessarily do it very efficiently. Oops. Now let's talk about the different ones. For capacitors, capacitors are very efficient. Best capacitors that we have are 99.9%. They're very good. They'll return a lot of energy. What's the problem with them? Oh, there are lots of different technologies and they tend to be rather temperature sensitive. So we have to look out for that. They do have a long life. That's a good thing. And in terms of cycles, it's reasonably unlimited for what you're going to do with it. Inductors have a long life. They're physically large. That's a problem. They have very low energy density. Capacitors are much better. Inductors have a very wide operating temperature range. They can, some of the insulation systems go up to 180 C. That's pretty hot. So they tolerate a lot of heat. And they have virtually unlimited cycles. Okay. Batteries, very efficient. What's the drawback? Short life. You got hand tools, good chance to use them much. You had to replace that battery. Okay, they just don't last that long. In cars, you know that's a big operating expense. You have to replace that battery. And it's expensive to do. That's a problem. Narrow operating range. They don't like temperatures. Batteries do not like low temperatures or high temperatures. And that's kind of true of anything that's chemically based. There are a limited number of life cycles on this thing. If you cycle it too much, any manufacturer of batteries are going to tell you it's good for so many cycles. Right, and then you're going to have to buy another one. One of the good things, if you don't know what UPS, that's uninterruptible power supplies. So this is kind of new with solar installations now. In the past, I think I told you in the beginning, you took the power from the solar array and you put it in the inverter and put it out on the line. So you weren't storing any power. If you have batteries as a energy storage cabinet, you have the ability to store energy during the day and use it at night. It also means, from the power company's point of view, they don't have to live with the wild swings of the output of the solar array. That's all goes into the battery, and the inverter puts out energy in a more controlled fashion. So the power companies like that. Now, if you're going to use your power for your own purposes, well, you know that the lights are going to go out at some point, right? Depending on the season, we're kind of what are we past the autumnal equinox? That was yesterday. Okay, so we're now on the downside of our daylight hours, and that's what's going to happen. Yes, sir.
Are capacitors used for homeowners often? I've only ever heard of batteries, but from this chart, it seems like they would be pretty good. You could insulate them and temperature control the room that they're inside.
The answer is yes, and in fact, they're customarily built into the inverter.
Oh,
So now, will they store enough energy to last for 12 hours. That would require a rather large capacitor. And it would probably become an economic problem rather than a technical problem.
Okay, so they'd be very efficient,
Yeah.
but it might be expensive to buy a big enough capacitor. Oh,
That's right. So, for their size, batteries do a good job. Yes, sir.
But what about multiple capacitors?
You would undoubtedly end up building something out of multiple capacitors. So, in terms of technology for capacitors, for their size, electrolytic capacitors really can't be beat in terms of for capacitors. Okay. Unfortunately, they're also the ones with the shortest life. And they have inside them an electrolyte that evaporates. And it evaporates faster when they get hot, which is why they don't like temperatures. So, and it's a pretty well-known wear-out mechanism. They're one of the few electronic components that has a well-known wear-out mechanism. Now, for semiconductors or electronic assemblies, thermal cycling is a life killer. And you're exercising things that have different coefficients of expansion, and you can break solder joints. You're familiar with tin whiskers. Tin can kind of grow and end up shorting out things. So silver migration, so when you start talking about something that lasts 20 years, you really have to look at the material properties of the thing of your design. If it only has to, if it's your cell phone, that's pretty much a don't care. You're not going to have it long enough to worry about most of those life limiting things. You're gonna get rid of it long before that happens. Okay. So batteries are a good thing to add to your solar installation. Now, having said that, it's probably going to add $9,000 or $10,000 to the price tag. So, but it allows you, particularly if you're living off grid, it gives you a way to store energy and use it in the off times. So, unless you just, when the lights go out, you're just going to go to bed and get up in the morning when the sun comes up. So, okay, this is kind of a block diagram. In the past, we had solar array, inverter, power grid. Very simple model. Power is generated and used in real time. Now, I've heard people say things like, well, we can just store energy on the grid. There's no such thing. Okay. Power on the grid is used in real time. So whatever you generate on the grid, it means somebody has to reduce the output because it's a balancing act. What gets used and what gets generated, what gets used has to balance. There's no storing AC power. So this is the improved version by using a battery. So you would run a battery charger, charges the battery, energy from the battery gets used by the inverter, it goes out to the power grid. Now this gives you a way to store energy and then release it in a more controlled manner. So, but there's a good chance you'll have to replace those batteries more than once. They're not going to last 20 years. That's a problem. Okay, this is kind of a comparison between the historical and the improved architecture. So historically, it was a very simple design, and it was a pretty reliable system. So if you notice, reliability kind of goes with the number of components of a system. So with the microinverter system, you heard me talk about that, about all of its advantages. You can have one panel, you get metrology on one panel. You have built-in redundancy, you can have mixer match panels. But if you have an array of 12 panels, you've got 12 microinverters. Okay, so having more components has the inherent disadvantage of making the system less reliable, just because of the component count. Okay, historically, cons, power delivery was time of day dependent. Okay, problematic with islanding systems. Okay, and what I meant by that is, if you're gonna live off the grid and get all your power from solar energy, if you don't have a way to store it or use it when the lights go out, that's kind of a problem. You're gonna have to have a backup generator or a backup grid or something else. Okay, so the improved system, better power delivery, fewer inverter dropouts. Remember I said that every time that inverter drops out, it's gonna wait 5 minutes to reconnect to the grid. It's waiting that 5 minutes, and that's part of the standard. That's not something you can arbitrarily change. Okay, that's what's built into the inverter. That's part of the grid tie standard. So if it drops out once an hour, you've lost 5 minutes of generation in an hour. Okay, batteries are very temperature dependent, and there is a higher cost associated with it. Talked about microinverters, string inverters. Talked about the pros and cons. Let's talk about monetizing your solar power. Okay, there's a couple ways you can do that. By law, the power company has to buy your power. Okay, so maybe you've heard the term net metering. So net metering means that you send power out to the grid and you draw power back from the grid. So, and you pay the difference, which sounds really good, except that the power company is not obligated to pay you what they charge you. Okay, they kind of pay you the wholesale rate, you pay the retail rate. So they're only required to pay you what's called the avoidance cost. So whatever it doesn't cost them to generate that kilowatt hour is what they pay. So, and if you look at your electric bill, anybody looked at their electric bill recently? I tend not to look at mine. I just look at the number and just pay it, right? But if you look at it, there's about 7 or 8 line items on it. And one of them is a connection charge. So they're charging you money to connect to their grid if you drew no power whatsoever, just for the privilege of being able to buy electricity from them. They're charging you to do that. There's a whole bunch of other things on there too, most of which sounds like I might know what they mean, but I really don't know. So net metering, maybe not such a good idea. I've heard it's kind of, in terms of popularity, it's kind of going away. The other is called a feed-in tariff. And what that means is you sell 100% of your electricity to the power company, and they pay you feed-in tariff. Now those feed-in tariffs can be really good. Years ago, they were as much as 50 cents, and that's not over the life of the product. Okay, that's not over the life of the cell. That may only be good for a year or two, and then they're going to change the feed-in tariff. And then you buy your electricity in the conventional way, just like you would. So you get some money and it offsets what you pay the electric company. Now, it's different in net metering in that net metering just directly subtracts it from what you're using. So another thing that's kind of become an area of concern. So a few years ago, we all started getting these electronic meters, right, for our house. And in a sense, well, it seems like a good idea. They don't have to send a guy out there to read the meter every month. Okay, they don't have to get bit by the dog or anything like that. They don't have to get out the weather. So if they can just go query your meter and find out what you used, that sounds like a good thing. Now, in the old way, where they sent somebody out there to read the meter, they would read the meter. And they would just subtract it from what they read last month, or subtract what was on the meter last month. And they go, okay, you used, 1,000 kilowatt hours, so we're gonna charge you for 1,000 kilowatt hours. Well, with the ability to read the meter comes something called time of usage charges, which means the cost of electricity is no longer flat. It actually changes depending on the time of day when you're using it. So the power companies understand the demand curves very well. So they know that when people get up in the morning, they're making breakfast, they're taking showers. So energy starts to spike up. In the middle of the day, it kind of comes down, and then it spikes up again in the evening when people come home, they're cooking dinner, and taking showers, and then they'll go to bed. That's when power usage is at its minimum. Well, think about your solar array. When is it putting out max power? Is it in the beginning? What's that? The middle of the day, when demand is really low. Okay, and they don't want your stinking power because demand is really low. So they may not pay you as much for it. So, and in the evening, when you wish you could use your own power, you got to go buy their power. So now this could be mitigated if you had a battery storage system that you could bank that energy in the middle of the day and use it when you needed it. That can mitigate that to a large extent. So time of use charges. So they may want to, I think they had a program where they would cut off your hot water heater for certain parts of the day. So it would reduce the demand on the grid. Things like electric cars and put new demands on the grid. You know what? There aren't a whole lot of new power plants built. So this is kind of a problem. So now something you may not know is that a lot of nuclear power plants are being recommissioned. So I have a friend who's a nuclear engineer. He kind of knows what's going on in that industry. Did you know the 3 Mile Island is being reactivated? And I believe it's for a server farm. So it was initially shut down because of, you might have thought it's because of the meltdown in reactor number 2, but it had a lot to do with the demand for the steel industry went away. So, but now there's a new server farm that needs lots of power. Anyway, I digress. Okay, feed-in tariffs for monetizing it. So the best way you can get money out of your solar panel system is actually to use it yourself. If you were off the grid, you're going to generate power, and then you're going to use it. Okay. May not be all that practical for you, but you wouldn't have to play the game. Now, the other thing that's going to come up is these systems last 20 years. Regulations change 20 years. So, okay. Talked about this. Feed-in tariffs, panels, 20-25 years. End of life. Okay, you're going to lose 0.5% per year. So end of life has a lot to do with mechanical failure and seals. Now, that doesn't mean that in 20 years your system is useless. Okay, it just means it's used its rate, you're up to its rated end of life. Think of all the things you use beyond their expected life expectancy, right? That closet of old shoes that are expired, right? And still use them for mowing the lawn or washing the car or whatever. Okay, it's not unusual for things to be useful beyond their rated end of life. So just because your system gets to be 25 years old, if it's still putting out power, you've long since paid for it. You may as well, having that old car. You ever heard of the term the golden mile? That's when you paid it off and you still have plenty of life left. So, okay. What else? Okay. The effects of insulation. Now this is kind of a, you can imagine the earth is the solid round circle in the middle, and the dotted line would kind of represent the atmosphere around the earth. So, and I put that in there to demonstrate that the sunrise in the morning, the sun is coming at a low angle, that's for sure. But you also notice that it passes through more atmosphere than it does at noon, because it's coming in at a lower angle. As the sun comes up to a higher angle, it has a path through the atmosphere is less. And also your latitude plays into that. So you know that as the earth goes around the sun, you know, it's got a 23.5 degree tilt. 23.5 degree tilt. Okay, so in summer, in the northern hemisphere, we're pointed toward the sun, and in the winter, we're pointed away from the sun. So what are you going to do with your solar panels? Ideally, they would be normal to the sun at all times. Now, there are things that called solar trackers, and companies make them. Instead of having a fixed array, you put the panels on this solar tracker, and what it does is it tracks the sun as it goes across the sky. Now, it's a big robotic thing, costs more money, and to be perfectly honest with you, the ROI is very questionable on it. So the idea, we know that as the sun goes across the sky, it gives us something that looks somewhat like a truncated sine wave. And if you could square that off, you could potentially get more energy. But the problem with the squaring off is it's usually at the morning or the evening, and you're losing light anyway for other reasons. So it's not as effective as you might think it would be. So solar trackers exist. They also have the ability to correct for the time of year. They can be more upright, change the angle. So as it turns out, the optimum angle, if you're going to have a fixed array, is really whatever your latitude is. You know, it's not going to be perfect for every day of the year, but it's the best compromise. Okay. So here's I made this. This is a daylight hours depending on your particular latitude. So you can see that for Oslo, their daylight hours go from over 20 down to less than 4. Okay, it's pretty dismal to be in Oslo in the winter. Okay? You know, the sun comes up at 10 o'clock in the morning and goes down at 2 in the afternoon. Okay, and in the summer, it doesn't really seem to go down at all. It just kind of becomes twilight for a while. And you can see that the lower you go in latitude, Salem, you can see we get a fair amount of day to night. Go south to Phoenix, it's a little bit better. And it kind of becomes, it's called the most optimal when you get around the equator. Okay, but it's also hot at the equator. Okay. What was one thing I was going to say? Okay, I'm going to talk for almost 2 hours. So, any final comments or questions? So, is this your salvation, or is this snake oil? Well, I think I'm going to have to leave that up to you. The cost of installations, I can tell you, have gone down compared to what they have been in the past. Now, parting comment. Putting a solar installation on your roof may not always be a good idea. I have a friend of mine who was looking into it, and what he found out was that his insurance company would have required him to put a new roof on the house. So if you have to put a new roof on the house to install your solar panels, that could be a nasty $20,000 addition to putting your solar panels. Another thing you might want to talk to as a realtor, if it's someday you're going to sell that house, those solar panels on the top of the house may not be the selling point you think it is. Okay, you may not be able to get a lot of value out of it. So if you have the room to put a ground level installation, you're probably ahead of the game. As far as putting one up on your own, I probably would recommend against that, because you have lots of codes, not only for electrical, but for mechanical. You've got to have sustain certain wind loading, and nobody wants the panels flying off to their neighbor's house. Yes, sir, you got a question?
Do you have any recommendations for local installer?
You know, I don't know any. Well, I know the people at Soul Coast. I know they do lots of things, not just solar. I would say shop around. Like anything, you're gonna find that it's not like everybody's the same price. You're gonna find a variety of prices. So,
I know a couple of people that have connections within the solar industry that when they have something like solar,
Yeah.
sure. So I will make this comment, and this is, I get that solar installers are there to make money, but we learned in trying to develop products for the solar market that that's where the money is made, in the installation. It's not in the manufacture of the goods. So I'm not saying you're dishonest people, but I'm saying go in with eyes wide open.
Yeah, it seems hard to find somebody who will do modular work as opposed to all of, they want to do everything.
Yeah. So I think we worked with a company in Eugene. I forget the name of them at this time. They're probably gone. Be wary of the promises that are made. You're going to pay for these things for a long time, and make sure that there actually is a return on investment. So, anything else? Yes, sir.
I have two things on, one on batteries. You know much about the advancement of sodium.
Sodium batteries?
Yeah, they lower energy density, but more, they're more stable across a wide temperature range and cheaper materials cost a lot. There's no risk of fire and that. Are you aware of
I have a
solar very often?
pardon?
Are you aware of that being used with?
I am not aware of them being used. So I don't know if they're, I know there's, I work with a company in Tualatin called Zinc 5. They make, it's not as good as lithium, but it's a very safe technology as well. And they're used for like server farm, backup for server farms. I'm not aware of any, I don't really have any intimate knowledge of the sodium batteries. I know we're looking at different technologies.
And the other question I had, when you mentioned the thermal, harnessing thermal energy produced by the solar panels, you said water would be a bad mix.
It could be a bad thing.
Does anyone try doing a non-conductive intermediate? So it'd be like a closed loop that would be pulling the heat off of the panels and then transferring that to a water source?
You know, I don't know of anybody who's doing it, but it seems like there's a lot of winds there in that design. And I don't know of anybody who's actually making solar hot water heaters either.
Seems like it would help also produce that 90 degrees, that 90 C.
Yes.
environment that that's like a big major concern on that side of the.
It is.
So that would be what would be double dipping on.
I actually bought a solar panel water heater for my house in 1985. And, you know, these energy crises seem to come around cyclically. This is at the tail end of the one from the late 70s and early 80s. And there was like a 40% tax credit. And it was a really good deal. And it was really about the time they were expiring. So they were really willing to make a good deal on that. It was a 4 by 10 foot copper panel. And it was an early system. It came with an 80-gallon tank. And let's just say it worked too good because we had to find uses for hot water. Otherwise, because it kept circulating through the panel, it just got hotter and hotter. So pretty soon we're washing with hot water and we're taking long showers, and you know, if you've got an abundance of hot water and it just keeps getting hotter, you got to use it for something. So, but this was in Florida too, so you got a lot of sun. So yeah, I had my one experience with that was that it worked really well. So, but it seems like a good marriage of solar thermal and solar electric.
I would encourage everyone if they have questions. I know,
Yeah.
Frazier, you have email that we can use to get a hold of you because you have a SWOCC email.
Yes, I do. You can feel free to contact me there. I also have a local consulting company, which is, I'm ashamed to say I don't check my SWOCC email as much as I probably should, but you can always get a hold of Dr. Corner. He knows where to find me. So.
Yeah, yes, we do, and we thank you. We thank you for your efforts there, Frazier.
Sure.
I thank every one of you for coming. And look for our next upcoming events. We have an upcoming planetarium show on October 2nd at the PAC that our student superintendent is actually going to be hosting. We have our next lecture series, I believe, is October 21st. When
I don't remember dates.
I do remember the October 21st part. Do you want to talk about something?
Yes, our geology speaker is Dr. Jeff Myers. He is a paleobotanist who just recently retired from teaching at Willamette University. And one of his claims to fame is he's the world expert on fossil Douglas firs, which is one of the things I'm hoping he'll talk about, because it turns out they're really weird and they're not fir trees.
Okay.
So join us for that, and join us for that on the 21st. More on that when we we'll have the press release probably out in the next week or so on that one. We will have we're looking at doing some K-12 STEAM events. Check our Facebook page at SWOCC STEAM Pathways and you'll get more information on that. And also send out press releases and all of that. You can inquire about about our STEAM Pathways program. You can contact Cassie, who was up at the beginning. Her extension here is 7416, or it's just cassie.clear@SSC.edu. You can also find any of us at our SWOCC emails, Aaron.Clear@SSC.edu, Linda Waffler, Derek Curley, Frazier, I think, is yours Frazier.Pruett or is it Henry.Pruett?
Henry.Pruett.
Okay. Feel free to send us any questions you may have. If you have ideas for speakers, send them our way too, because we can always look for potential options. And with that, thank you guys for attending.
Yeah, thank
See
you.
you next time. If you didn't sign in, please remember to sign in the sign-in sheet, and we have business cards there on the sign-in table as well.
This summer, I've been all over summer. I don't know where it's yet, so that's.